Right now, you are sitting still, but zoom in, closer, past your skin, past your atoms, past the tiny sparks buzzing inside them. Keep going, smaller and smaller, until you slam into a wall where space itself stops making sense. Scientists call it the Planck length, the smallest size that can ever exist, and below it, reality falls apart. Down here, empty space boils like water. Time stutters and skips. Tiny black holes flicker in and out of nothing. Some scientists think space is woven from invisible threads. Others think the whole universe is a code painted on a distant surface. If your brain enjoys being bent, subscribe and ride with us. We're about to shrink past the smallest thing that can ever be measured. Hold on tight, we begin. Grab the smallest thing you can imagine, then cut it in half. Now cut that half in half, do it again and again. Nothing stops you, right? You could keep slicing forever, down and down, into pieces too tiny to name. That's what almost everyone believes about space. It feels endless, like a hallway of mirrors going down with no bottom floor. For thousands of years, the smartest people alive agreed. Space was smooth. Space was continuous. You could always find a smaller step, a shorter distance, a tinier gap. Cut a grain of sand, and inside there is always room to cut again. The ancient Greeks argued about it. The great thinkers who built modern physics assumed it. Smooth all the way down, forever. Then the 20th century arrived and two giant ideas crashed into each other. The first idea was gravity, the way huge objects like stars and planets bend the space around them. The second idea was the quantum world, the strange rule book that controls the tiniest specks that exist. On their own, each idea works beautifully. Gravity predicts how galaxies swing. The quantum rulebook predicts how a single speck of light behaves, and it gets the answer right to more decimal places than you could check in a lifetime. But squeeze both ideas into the same tiny spot, and they start screaming at each other. Here is the trouble. Gravity likes space to be smooth and calm, a gentle bending sheet. The quantum world is wild and jumpy and never sits still. When you zoom down far enough, the quantum world starts shaking space so hard that the smooth sheet buckles. The math that worked so well suddenly spits out nonsense. Numbers blow up to infinity. Equations that predicted the universe now predict garbage. Think of a photo on your phone. From far away it looks perfect and smooth, but zoom in and zoom in more, and eventually you hit the pixels. The smooth face becomes a grid of tiny coloured squares. Zoom past that and there is nothing smaller to see. The picture simply runs out. Physicists began to wonder if the universe does the same thing. What if space also runs out of smaller pieces? What if there is a real bottom, a shortest possible distance, a smallest possible gap, below which the word smaller stops meaning anything at all? This is one of the biggest questions in all of science, and it is still not fully answered. Nobody has a machine that can look that deep. Nobody has a photo of the bottom of space. What we have is a number, a single, precise number that the math keeps pointing to, over and over, from completely different directions. Every road leads to the same tiny size. Try to measure anything shorter, and the universe stops cooperating. Try to fit inside a smaller space, and reality itself pushes back. It is as if the cosmos has a fence built into it, a line drawn in the fabric of everything, and it will not let you cross. That fence has a name. It was discovered more than 100 years ago by a quiet man doing math about light and heat. A man who had no idea he was mapping the edge of space. He found the exact size of the wall at the bottom of the universe, and once you learn how small it truly is, your idea of small will never feel the same. His name was Max Planck, and in the year 1900 he was not hunting for the edge of space. He was trying to solve a boring problem about how hot objects glow. A piece of metal in a fire turns red, then orange, then white as it heats up. Planck wanted the math behind that colour change, and to get it, he was forced to imagine something wild. He guessed that energy did not flow smoothly. It came in tiny packets, like coins instead of a river. That single guess cracked open the entire quantum world and changed science forever. But hidden inside his work was something even stranger, and it took years for people to notice. Planck realized he could combine three of the deepest numbers in all of nature: the speed of light, the strength of gravity, and the size of those tiny energy packets. Three numbers that rule the whole universe. When he mixed them together in a certain way, out popped a length, a specific distance, a size that came from nothing but the raw settings of reality itself. This size did not depend on rulers or humans or Earth. Any alien on any planet doing the same math would find the exact same number. It is baked into the cosmos. Today we call it the Planck length, and it may be the shortest distance that can exist. Here is what makes it so haunting. Every serious attempt to build a theory of the smallest scale runs face first into this length. Try to describe space below it, and the equations break. Try to measure anything shorter, and the tools fail. It shows up whether you use gravity, whether you use the quantum rules, whether you use string theory or loop theory or something else entirely. Scientists have not confirmed that space truly stops here. That part is still a mystery. But almost every theory agrees on one thing. Something important happens at the Planck length, and it is unlike anything happening at larger sizes. This is the doorway. Cross it, and the ordinary picture of smooth, calm space simply stops working. To feel why this matters, picture a ruler. A normal ruler has lines for inches. A better ruler has lines for tenths of an inch. The best ruler in a lab can measure widths thousands of times smaller than a human hair. Scientists have machines that can sense a single atom, a speck so small that millions would fit across the width of this letter. And the Planck length makes an atom look like a galaxy. That is the part nobody's brain can hold. We're not talking about a little smaller than an atom. We're not talking about 1,000 times smaller or 1,000,000 times smaller. The gap between an atom and the Planck length is so enormous that comparing them almost breaks the meaning of the word small. Planck himself barely spoke about it. He filed the number away as a curiosity, a strange leftover from his equations, and moved on. He could not have known he had stumbled onto what might be the smallest possible size in existence, the last step down before the floor of the universe. For decades the number sat quietly in textbooks, ignored, waiting. Then physicists trying to unite gravity and the quantum world dusted it off and gasped. Because when you actually write out how tiny the Planck length is, with every single zero in front of it, the number stops feeling like a measurement. It starts feeling like a warning. Let's write it out, because you have to see this with your own eyes to believe it. Take 1 meter, about the length of a big step, or the height of a kitchen counter. Now shrink it down to the Planck length. To do that, you write a decimal point, then 34 zeros, and then finally a 1. 34 zeros of pure nothing before you even reach a single digit. That number is so far below everything you know that ordinary comparisons fall apart. So let's build a ladder and climb down it, one impossible rung at a time. Start with a human hair. It looks thin, but under a microscope it is a thick rope. Now go smaller to a single cell in your body, thousands of times thinner than that hair. Smaller still to a single molecule of water. Smaller again to one atom, a speck so tiny that if you lined up 10 million of them, they would barely stretch across the period at the end of this sentence. You would think an atom is basically the bottom. It is one of the smallest things anyone has ever pictured. But we have only just begun to fall. Inside the atom is a nucleus, a tight little core, and it is about 100,000 times smaller than the atom around it. If the whole atom were a giant football stadium, the nucleus would be a single marble sitting on the centre of the field. And inside that marble are even smaller specks, the tiny bits that build the core. Keep dropping, past the specks inside the core, down and down through 20 more levels of smallness, each one shrinking by a factor most people cannot imagine. Only after all of that, far, far below the smallest thing any machine has ever touched, do you finally reach the Planck length. Here is a comparison that might help it land, though even this barely works. Imagine you could grab a single atom and blow it up until it was as wide as the entire visible universe, billions of light years across, so huge that light would need billions of years just to cross it. Stretch one tiny atom to that unthinkable size. Now, inside that universe-sized atom, How big would the Planck length be? About the size of a football field. Read that again. Blow one atom up to the size of everything we can see, and the smallest possible distance is still just a strip of grass where a game is played. That is how deep the Planck length hides beneath the world you live in. No microscope will ever show it. No machine humans could build, not even a machine the size of a planet could zoom in that far. It is thousands of trillions of times below the reach of our best instruments, and it may stay that way forever. This part is not a theory or a guess. The math is solid and confirmed. The Planck length is simply, brutally, unreachably small. And yet, this is the size where the deepest secrets of the universe are hiding. Space, time, gravity, the very fabric of everything. All of it may be built out of pieces this small. The strangest part is what happens if you actually try to reach down there and take a look. Because nature does not just make the Planck length hard to see. Nature fights back. And the way it fights back is one of the most bizarre traps in all of physics. You might think the only problem with seeing the Planck length is that our tools are too weak. Build a better microscope, wait a few centuries, and surely we crack it open. That feels reasonable. It is also completely wrong. The problem runs deeper than technology. Nature itself refuses to let you look that closely, and understanding why takes us into one of the sneakiest rules in all of science. To see something small, you have to hit it with something even smaller. This is how all seeing works, even your own eyes. Light bounces off an object and into your eye, and your brain reads the pattern. That works fine for big things. But light comes in waves, and every wave has a length, a distance from one ripple to the next. You cannot use a wave to measure something smaller than the wave itself. It is like trying to feel the shape of a grain of sand while wearing thick winter gloves. The tool is too clumsy for the target. So to study tiny things, scientists use tinier waves, and here is the rule that ruins everything. Tinier waves carry more energy, much more. To see something at the level of an atom, you need a wave so sharp and so packed with energy that scientists build machines miles long just to make it. These machines, called particle colliders, are among the largest devices humanity has ever created, and even they only scratch the surface of smallness. Now push this to the limit. To see all the way down to the Planck length, you would need a wave with a shorter ripple than anything that has ever existed, and that wave would carry an amount of energy so gigantic it defies imagination. Watch what happens next, because this is where nature laughs at us. You aim your impossibly powerful wave at a single Planck-sized spot, hoping to snap a photo. But you have just crammed a mountain of energy into a space smaller than anything. And energy, thanks to one of the most famous ideas in physics, is the same thing as mass. Squeeze enough energy into a tiny enough spot, and it behaves exactly like a heavy object. In fact, it behaves like the heaviest, densest object the universe knows how to make. The light you fire does not reveal the Planck length. Instead, the energy of that light collapses in on itself. The spot you are trying to photograph gets so crushed that space bends completely around it, folding shut like a mouth closing. You do not get a picture. You get a trap that swallows your light, your wave, and any information you hope to gather. Scientists are confident about this reasoning. It comes straight from combining gravity with the quantum rules, and the two agree perfectly here. The closer you try to look, the more energy you need, and the more energy you use, the more violently space collapses to hide the very thing you wanted to see. It is the ultimate locked door. The harder you push, the tighter it seals. Nature has built a defense against curiosity right into the fabric of space, and the Planck length sits safely behind it, forever. But what exactly is that trap that forms? What is this thing that eats your light the instant you look too closely? It has a name you already know, and it is far stranger than most people realize. The trap that snaps shut when you look too closely is a black hole, a real one, born in the blink of an eye, smaller than anything you can picture. Everyone has heard of black holes as giant monsters in space, dead stars so heavy that light cannot escape them. That is true, but it is only half the story. A black hole is really just a rule about squeezing. Take any amount of stuff, cram it into a small enough space, and it will collapse into a black hole. The heavier the stuff, the more room it gets before it collapses. The lighter the stuff, the more brutally you have to squeeze. This means you could make a black hole out of anything, even a feather, even a single beam of light, if only you could squeeze it hard enough. And when you try to probe the Planck length, that is exactly what you do. You squeeze so much energy into so tiny a spot that a microscopic black hole forms right there, instantly. Picture the smallest possible black hole the universe allows. Its size is, unsurprisingly, right around the Planck length. It is so small it makes an atom look like the sun. And the moment it appears, it does what all black holes do. It hides everything inside a wall that no light and no signal can ever cross. So every time you reach down to the Planck length, space punishes you the same way. You do not see a tiny piece of the world, you accidentally create a tiny black hole, and it swallows the answer whole. Look closer, make a bigger squeeze, make a bigger black hole. The mystery pulls its own curtain shut, every single time. This is the deep reason so many scientists believe the Planck length is a true bottom. It is the size where the act of measuring destroys the thing being measured. Below it, the words distance and location may simply lose all meaning, because any attempt to pin them down collapses into a black hole and erases the question. Here is a comparison to feel it. Imagine trying to study a soap bubble by poking it with your finger. The gentlest touch pops it. There is no way to feel its surface without destroying it. The Planck length is like that, except 1,000,000 times worse. The bubble does not just pop, it vanishes behind a wall that nothing in the universe can open. Now this reasoning is confirmed by the math, and scientists across the world agree on it. Where they disagree, wildly, is on what it means. Some say it proves space has a smaller size, a true grain, and there is nothing below the Planck length at all. Others say space might still be smooth down there, but forever hidden from us, locked away where no experiment can ever go. That argument is still raging, and nobody has won. But there is one more twist, and it is the strangest yet. These tiny black holes may not just appear when we try to look. Some physicists think they are popping up on their own, right now, everywhere, billions upon billions of them, flashing in and out of existence faster than any clock could catch. If that is true, then empty space is not calm. Empty space is not still. At the smallest scale, the ground beneath everything may be shaking, churning, and boiling with a violence that would terrify you if you could see it. Before we watch space boil, we have to face a rule so strange that even the scientists who discovered it argued about it for years. It says the universe has a built-in blurriness, and no amount of effort can ever sharpen it. The rule comes from the quantum world, and here is the simple version. You can never know everything about a tiny thing at once. The more exactly you pin down where a speck is, the more its speed becomes a wild guess. The more exactly you measure its speed, the more its location smears into a fog. Nature refuses to hand you both answers with full sharpness. It is a trade, forced on you, and you cannot escape it. This is not because our tools are bad. It is a deep law woven into everything. Even a perfect machine, built by a perfect engineer, would hit this blur. Scientists have tested it countless times, and it holds every time. This part is rock solid, confirmed beyond doubt. For big objects, the blur is far too small to notice. Your car has a position and a speed, both crisp and clear, because the blur only shows up for the tiniest specks. But now shrink down toward the Planck length, and the blur stops being a tiny detail. It grows into a raw. Think of it like a photo taken by a shaking camera. Hold the camera steady and the picture is sharp. Let your hand tremble and everything smears. At normal sizes, the universe holds the camera steady. But down near the Planck length, the camera shakes so hard that the idea of a clear picture falls apart. Positions blur into other positions. Here bleeds into there. The very meaning of exactly where dissolves, and this blur feeds directly into everything from earlier. If you cannot know exactly where something is, then energy itself gets fuzzy too. The rule says energy can flicker and jump for tiny moments, borrowing from nowhere and paying it back before the universe notices. The smaller the patch of space, and the shorter the moment, the more violently energy is allowed to swing. At the Planck length, those swings become enormous. Energy flickers so hard that, as we saw, it can crush space into tiny black holes. So the permanent blur is the engine behind the boiling. The smaller you go, the wilder the flicker, until calm, empty space becomes a storm. Here is the number that stuns people. This blur has always been here. It was here before you were born. It is here inside you right now, inside every atom of your body, humming at a level far too small to feel. The chair you sit on, the air you breathe, the light in this room, all of it rests on top of a foundation that is fundamentally, permanently unclear. The solid world is a calm surface floating on a shaking sea. Most scientists accept the blur completely. What they cannot agree on is how bad it gets at the very bottom. Some think it stays somewhat gentle. Others think it goes totally wild, ripping and reforming space faster than thought. Nobody has looked down there to check, and thanks to the trap we met earlier, nobody may ever be able to. But if the wildest guess is right, then the smallest scale of space is a place of pure chaos, a place where a strange froth churns and bubbles, tearing holes in the universe and stitching them shut again, over and over, forever. Scientists gave that froth a name, and picturing it may change how you see the empty air in front of your face. In the 1950s, a brilliant and playful physicist named John Wheeler tried to picture what space looks like at the smallest scale. He was the kind of thinker who invented vivid names for wild ideas, and the name he chose for this one stuck forever. He called it quantum foam. The picture is unforgettable. Look at the ocean from an airplane miles up. It looks flat, calm, and smooth, a sheet of blue glass. That is space at normal sizes, the space you walk through every day. Now drop down to the surface of that same ocean during a storm. Suddenly you see chaos. Waves crashing, spray flying, bubbles forming and popping, foam churning everywhere. Nothing is smooth, nothing holds still. Wheeler said space is the same. From far away, meaning at the sizes we live in, it looks perfectly smooth. But zoom down to the Planck length, and that smoothness shatters into a raging froth. Tiny bubbles of space form and vanish. Little pockets twist and pinch. The whole fabric writhes, churning like storm foam that never settles. And these bubbles are not gentle. Remember the tiny black holes from before, and the wild energy flickers, and the permanent blur. Wheeler's foam ties them all together. In this picture, space at the smallest scale is constantly ripping open into tiny black holes and pinching off into little loops, then healing shut a moment later. Structures appear and disappear so fast that no clock could ever catch them in the act. Here is a comparison to hold on to. Imagine a pot of water at a rolling boil. Bubbles are born, rise, and burst, again and again, so quickly the surface is a blur of motion. Now shrink that boiling pot down past the atom, past everything, all the way to the Planck length. The bubbles there are not made of water or air. They are made of space and time themselves, boiling in and out of existence. This means the empty space in front of your face, the air you would call nothing, is not truly empty at all. Deep down, far below what any eye can see, it seethes, it roils. A single grain of what looks like nothing is secretly a storm of unthinkable violence, held far beneath the sizes you can ever touch. Now here is the honest part. Quantum foam is a theory, not a proven fact. No one has ever seen it, because of the trap we already met. The moment you try to look, you make a black hole, and the view slams shut. So the foam remains an idea, a strong and beautiful guess built from combining gravity with the quantum rules. Many scientists believe some version of it must be true. Others think the foam might be gentler, or shaped differently, or maybe not there at all. But the idea refuses to die, because it keeps solving problems. It hints at where matter comes from, why empty space carries energy, and how the universe might have begun. If the foam is real, then it is the true face of reality, hiding under everything, a churning sea that builds the calm world we mistake for solid ground. And that raises the deepest question of all. Is space really made of these boiling bubbles, actual tiny pieces with the smallest size? Or is it smooth all the way down, a perfect sheet with no grain at all? This single question splits the world's greatest physicists into two warring camps, and the fight between them is far from over. Two ideas about space are locked in a battle that has lasted for decades, and the winner will reshape how we understand everything. On one side stands the belief that space is smooth. On the other stands the belief that space is grainy. Both cannot be right, and the world's best minds are split down the middle. The smooth camp says space is like still water in a glass. Pour it, and it flows without any gaps. Cut it anywhere, and you can always cut smaller. There is no smallest piece, no true grain, just an endless, seamless sheet that goes down forever. This is the idea that ruled science for centuries, the one built into the equations that describe gravity so beautifully. In this picture, the Planck length is just the size where our tools and theories fail. Space itself keeps going, smooth and unbroken, below it. The grainy camp says space is like a beach. From far away, a beach looks like a smooth tan blanket. But kneel down and it breaks into countless separate grains of sand, each one a tiny piece with a definite size, with gaps between them. Grab a smaller and smaller scoop, and eventually you cannot go smaller. You hit a single grain, and that grain cannot be split. In this picture, the Planck length is a real flaw. Below it, there is no below. Space simply comes in smallest possible chunks, and that is the end. The stakes could not be higher. If space is grainy, then reality has a smallest size, a shortest step, a true bottom. Time itself might come in ticks. Motion might happen in jumps. The universe would be less like a flowing river and more like a giant board game, played out square by square on a grid too fine to ever see. Here is what makes the fight so fierce. Both sides have powerful math on their team. The smooth idea gives us the equations that predict how planets orbit and how the whole universe expands, tested and confirmed thousands of times. The grainy idea offers a way to finally tame the wild infinities that appear when you try to mix gravity with the quantum world. When space is grainy, those blow-ups vanish, because you can never get infinitely small. Scientists have not settled this. It is one of the great open mysteries of physics, and honest researchers on both sides admit they do not know the answer yet. The trap we met earlier is the reason. We cannot simply look and check, because looking that close collapses everything into a black hole, so the debate rages on in equations and theories, waiting for some clever experiment to break the tie. But the grainy idea has been gaining strength. More and more physicists suspect that space really does come in pieces, that the smooth sheet is an illusion, the way a movie looks smooth even though it is really thousands of separate still frames flashing by. Get close enough and the flow breaks into steps. If they are right, it forces a mind-bending question. What would it even mean for space to be made of pieces? What are the pieces made of? How do they connect? And could the universe you live in really be built like a screen, out of countless tiny dots, each one a single grain of existence? That question leads to one of the boldest ideas in all of modern science, an idea that says reality might work more like a computer than anyone ever dared to guess. Look very closely at any screen, your phone, your television, a giant billboard. Press your eye right up to it. The smooth flowing image shatters into thousands of tiny glowing squares. Pixels. Each one is a single dot of colour, and there is nothing smaller on the screen. The picture only looks smooth because the pixels are so tiny that your eye blends them together into one seamless whole. Some scientists think the universe works the exact same way. In this bold idea, space is not a smooth sheet at all. It is a grid, an unthinkably fine grid of tiny pieces, each one about the size of the Planck length. What looks like smooth, flowing space is really countless tiny cells packed together so tightly that you could never spot the seams. You move through a room and it feels like gliding, but down at the bottom, you might be hopping from one cell to the next, like a character stepping across squares on a game board. If this is right, the effects are staggering. Motion would not be smooth. It would happen in the smallest possible steps, jumps too tiny to ever feel. A ball rolling across the floor would really be flickering forward, square by square, faster than any measurement could catch. Even the light entering your eye right now would be moving in tiny hops across a grid so fine it hides from every machine ever built. Here is a comparison that fits perfectly. Think of an old cartoon. It looks like the characters move smoothly, but they do not. The cartoon is really a stack of separate drawings, flashed one after another so fast your brain fills in the motion. There is no true smoothness anywhere. There is only a series of frozen frames. The pixel universe says reality is built the same way, out of tiny still pieces, blurred into fake smoothness by their impossibly small size. This idea excites many scientists because it hints at something wild. If space comes in smallest pieces, and time comes in smallest ticks, then the universe starts to look a lot like information, like data. Like a colossal computation running on a grid, each Planck-sized cell holding a tiny scrap of the whole. Some physicists have wondered, half seriously, whether reality itself behaves like the biggest computer imaginable, crunching the state of everything one Planck step at a time. But honesty matters here, so let's be clear. Nobody has proven any of this. The pixel universe is a theory, a striking guess, not a confirmed truth. Space might be grainy in a much stranger way than a simple grid, or it might not be grainy at all. The pixel picture is a helpful way to imagine graininess, but real space, if it is chunky, is probably far weirder than the neat squares on your phone. Still, the idea has teeth. Scientists have even hunted for its fingerprints. If space were a grid, then light racing across the universe for billions of years might get subtly tripped up by the tiny cells, arriving a hair late or slightly scrambled. Researchers have watched ancient light from far-off cosmic explosions, searching for exactly this. So far, the results are murky, and the hunt continues. Yet the pixel idea, as bold as it is, might still be too simple. Because one of the leading grainy theories says space is not built from squares or cubes at all. It says space is woven, like fabric, from invisible threads, knotted and looped together in a pattern more beautiful and stranger than any grid. Imagine reaching out and touching a shirt. It feels like a smooth, solid sheet. But bring it close to your eye, and you see the truth. It is not solid at all. It is thousands of thin threads, woven over and under each other in a tight pattern. The smoothness was an illusion, created by threads too fine to notice. One of the leading theories about the smallest scale of space says the universe is woven exactly like that shirt. This theory is called loop quantum gravity, and its idea is breathtaking. It says space is not a smooth backdrop that things sit inside. Instead, space is made of countless tiny threads, or loops, linked together into a vast web. These loops are about the size of the Planck length, the smallest possible size. Weave enough of them together, and their pattern creates the thing we call space. The smoothness you feel is fake, the same way the smoothness of a shirt is fake. Get close enough, and it all breaks into threads. This flips everything you thought you knew. Most people picture space as an empty container, a big room that stars and planets float around in. Loop quantum gravity says there is no room, there is no container. Space itself is the web. Take away the loops, and there is no empty space left behind, because the loops were the space all along. It is like asking what is behind a shirt once you remove every thread. The answer is nothing, because the threads were the shirt. Here is why scientists take this seriously, even though it sounds like a dream. When you build space out of loops, one of the biggest problems in physics quietly disappears. Remember how mixing gravity with the quantum world spits out infinities, numbers blowing up to nonsense? Those infinities came from letting things get infinitely small. But if space is made of loops, nothing can be smaller than a loop. There is a true smallest size. The infinities have nowhere to go, and they vanish. That is a huge win. It is one of the main reasons this theory has survived and grown for decades, championed by serious physicists around the world. But be careful, because this is still a theory, not a confirmed fact. No one has ever seen a loop. No machine can reach the Planck length to check. Loop quantum gravity competes with other ideas, and the debate over which one is right remains wide open. What makes it exciting is that it paints a clear, testable picture, and clear pictures can eventually be proven or broken. The picture goes even deeper than simple threads. The loops do not just sit there in a plain weave, they connect at points, and they cross in specific ways, forming a web with a hidden structure, a kind of map that describes exactly how each piece of space links to the next. This map is the real skeleton of reality in the theory, more fundamental than space itself. Scientists gave this hidden web a name, and studying it reveals something that sounds impossible. If loop quantum gravity is right, then space is built from objects so basic that they are, in a very real sense, the true atoms of space. Not atoms of matter, like the ones in your body. Atoms of space itself. And these atoms of space have properties so strange that they force us to rethink what area and volume even are. You know that matter is made of atoms. Your hand, this air, the whole planet, all of it is built from tiny building blocks. But loop quantum gravity says something far wilder. It says space itself has building blocks, not the stuff inside space. Space, the emptiness, the room, the very thing everything else sits in. To describe these building blocks, scientists draw something called a spin network. The name sounds scary, but the picture is simple, and once you see it, you will never forget it. Imagine a web of dots connected by lines. Each dot is a tiny grain of space, a smallest possible chunk of volume, roughly the size of the Planck length cubed. Each line is a connection, a link showing which grains touch which. String enough of these dots and lines together, and their pattern builds up into the space you walk through every day. The web is the skeleton of reality. Everything you see rides on top of it. Here is the mind-bending part. In this picture, a single grain of space is not sitting somewhere. It does not have a location, because location only exists once you have space. And the grains are what make space in the first place. The grains come first. Position comes second. It is like asking where a single brick is before the house is built. The brick is not anywhere yet, it is just a brick waiting to become part of a place. Let's make this concrete with a comparison. Think of a social network, the kind on a phone. Each person is a dot. Each friendship is a line connecting two people. The whole network is just dots and lines, a pattern of who is connected to whom. Now imagine that pattern is not describing people, it is describing space. Each dot is a grain of space, each line is a neighbour, and the entire universe is one gigantic web of connections, unthinkably vast, woven from Planck-sized threads. This means the space in your bedroom, which feels so smooth and empty, is really a dense tangle of grains, billions upon billions of them, more than there are stars in every galaxy combined, all packed into a space smaller than a single atom. The emptiness is a lie. It is the fullest, busiest thing imaginable, just built at a scale far too small to ever glimpse. Scientists find this idea powerful because the web can bend, twist and rearrange, and when it does, that is what we experience as gravity. A heavy star does not warp some smooth, invisible sheet. It rearranges the web of grains around it, changing how they connect. Gravity becomes a change in the pattern of the atoms of space. Now the honest reminder, because it always matters, spin networks are part of a theory that no one has confirmed. Beautiful math, yes. Proof, not yet. The atoms of space might be real, or they might be a clever description that later gets replaced by something even deeper. Physicists are still testing, still arguing, still searching for any experiment that could catch a whisper of the web. But if it is real, something astonishing follows. If space is made of countable grains, then space can be counted. And if it can be counted, then the size of anything, its area, its volume, might not be smooth and flowing after all. The size of a thing might come in tiny fixed steps like coins in a jar, with nothing allowed in between. Here is a question that sounds too simple to matter. How big is a surface? Take the top of a table. Its area is just how much flat space it covers. You would guess that area can be any size at all. Make the table a hair bigger, and the area grows a tiny bit. Shrink it a hair, and the area drops a tiny bit. Smooth, continuous, any value you like. Loop quantum gravity says no. And its answer might be the strangest thing yet. In this theory, area cannot be just any size. Area comes in smallest possible chunks, like money. Think about coins. You can have 1 cent, or 2 cents, or 3 cents. You can never have half a cent because the smallest coin is 1 cent and nothing smaller exists. Money comes in steps, not a smooth flow. Loop quantum gravity says surfaces work the exact same way. There is a smallest possible area, a single grain of surface, and every real surface must be a whole number of those grains. Nothing in between is allowed. The smallest chunk of area is tiny beyond belief, right around the Planck length squared. So for everyday things, the steps are far too small to notice. A table looks perfectly smooth in its sizes because the grains are so fine that trillions of them make up even a fingernail. But the steps are still there, hidden underneath, and they are real in the theory. Area does not flow. It clicks, one grain at a time. Volume works the same way. The amount of room inside a box cannot be just any value. It comes in smallest possible pieces too, tiny grains of volume, and every real volume is a whole number of them. You cannot have a fraction of a grain, the same way you cannot have a fraction of a coin. Space itself is chunky, all the way through. Let this settle in, because it changes the whole picture. If area and volume come in fixed steps, then reality is far more like a board game than a flowing river. The universe would have a smallest square of surface and a smallest cube of room. Everything larger is built by stacking these pieces one at a time with no smooth in between. The world would be digital at its deepest level, counted out in the smallest possible units, like a picture built from pixels that can never be split. Here is a comparison to lock it in. Think of building anything out of tiny plastic blocks. You can make a wall 2 blocks wide or 3 blocks wide. You can never make it 2.5 blocks wide because you cannot break a block in half. The blocks are the smallest unit and every shape must be built from whole ones. Loop quantum gravity says the universe is built from blocks like that, so small that the whole world looks smooth, even though it is really counted out block by block. Now, the reminder you know is coming. This is a theory, a powerful, careful, respected theory, but not a confirmed truth. No experiment has ever measured a grain of area or a chunk of volume, because they are so far below our reach. If loop quantum gravity is right, though, then the smoothness of everything is the grandest illusion in existence. And if space comes in smallest chunks, then a haunting question follows immediately. What about time? Does time also come in smallest pieces? Is there a shortest moment, a single tick, below which the word sooner has no meaning at all? If space has a smallest possible size, then it feels almost forced to ask the twin question. Does time have a smallest possible piece too? Is there a shortest tick of the universe's clock, a moment so brief that nothing shorter can exist? Physics has an answer waiting, and it comes straight from Max Planck's old math. Mix the same deep numbers together in a slightly different way, and out pops not a length, but a time. Scientists call it the Planck time, and it may be the shortest moment that can ever pass. How short is it? Take the Planck length, the smallest distance, and ask how long light takes to cross it. Light is the fastest thing in the universe, so nothing crosses that gap quicker. The time light needs to travel one Planck length is the Planck time, and it is so brief that no word for fast comes close. Let's try to feel it. In 1 single second, light can travel around the entire Earth about 7 times. That already sounds impossibly fast. Now here is the shock. The number of Planck times that fit inside 1 ordinary second is larger than the number of seconds that have passed since the universe began. Read that slowly. More tiny ticks fit in 1 heartbeat than there have been seconds in all of history, stretching back billions of years to the beginning of everything. That is how fine time might be chopped. If the Planck time is a true tick, then everything you experience as smooth-flowing time is really a rapid-fire series of moments, clicking past one after another, far too fast for any clock to catch. Time would not glide like a river. It would flicker like a film, one frozen frame after the next, blurred into fake smoothness by sheer speed. Here is a comparison to hold on to. Think again of a movie. It looks like continuous motion, but it is really a stack of still pictures, flashing by so fast your brain fuses them into flow. If the Planck time is real, the universe runs the same way. Reality is a cosmic movie, and each frame lasts exactly 1 Planck time. Between 2 frames, there is no between, because a shorter moment does not exist. This idea ties directly to grainy space. If space comes in smallest chunks, it makes deep sense that time comes in smallest ticks too, because space and time are woven together into one single fabric. You cannot chop up one without touching the other. So the theories that make space grainy tend to make time grainy as well, one tick at a time. Now the honest truth, as always, the Planck time is real math, and the number is solid and confirmed, but whether it is a true smallest tick, an actual floor below which time cannot be divided, remains an open mystery. Some scientists believe time truly comes in these ticks. Others think time might still be smooth down there, even if space is not. Nobody has looked, because the Planck time is even further beyond our reach than the Planck length. Yet if time really does come in ticks, it forces us to a startling place. It means the universe has a shortest possible event, a single frame of existence, and that idea takes us back to the most important tick that ever happened. The very first frame of the universe, right at the beginning of everything, wind the clock of the universe backward. Watch galaxies rush together. Watch stars melt back into raw hot gas. Watch everything crush closer and closer, hotter and denser, running the story of the cosmos in reverse, all the way back toward the very beginning. Back to the moment the universe was born. You are heading for the Big Bang, the birth of space and time, and as you rewind, you slam into a wall made of time itself. That wall is the Planck time. Here is what it means. Scientists can describe the history of the universe with astonishing confidence, almost all the way back to the start. They can tell you what the cosmos was doing 1 minute after the beginning, 1 second after, even a tiny fraction of a second after. The story holds together beautifully, tested against the light and matter we see today. But there is one stretch they cannot describe. The first sliver of existence, the span from the very start of time until 1 Planck time had passed. This is the earliest moment physics can even talk about, the first frozen frame of the cosmic movie. Before it, the equations break. The known laws stop working. It is a curtain drawn across the birth of everything, and no one has managed to peek behind it. Why does it break there of all places? Because at the first instant, the entire universe was squeezed smaller than an atom, smaller even than the Planck length. And when the whole cosmos is crammed into a space that tiny, gravity and the quantum world are forced together with maximum violence. That is exactly the clash we have chased this whole time. The clash that spits out infinities and nonsense. At the birth of the universe, the two greatest theories in physics both fail at once. So the Planck time marks the true edge of knowledge. Not the edge of the universe in space, but the edge of the universe in time. It is the closest we can get to the beginning before the map runs out and turns blank. Here is a comparison to make it land. Imagine watching a video of a glass shattering, then playing it in reverse. The pieces fly back together into a whole glass, smoothly, clearly, easy to follow. But right at the very last instant, just before the glass becomes perfectly whole, the video freezes and cuts to black. You never see the final moment. You know it happened, but the recording refuses to show it. The Planck time is that black cut, placed at the birth of everything. Scientists agree completely that this wall exists. Where they split is on what lies behind it. Some think a bigger theory, one that finally unites gravity and the quantum world, will pull the curtain aside and reveal the true first instant. Others wonder if the question even makes sense, if asking what happened before 1 Planck time is like asking what is north of the North Pole. There may simply be no before. That thought is dizzying. It suggests time itself might have limits, a first tick with nothing before it, and it raises an even stranger possibility, one that turns everything upside down. Maybe, at the smallest scale, time does not just have a shortest tick. Maybe time stops meaning anything at all. We treat time as the one thing we can always count on. The past is behind us. The future is ahead. Moments march forward in a neat, steady line, one after another, never skipping, never stopping. It feels like the deepest truth there is. But at the smallest scale of space, that steady march may completely fall apart. Here is the problem. Everything we have learned points to the same wild conclusion. Down near the Planck length, space is a churning foam, boiling and twisting, ripping open and healing shut. And space and time are woven together into one fabric. So if space is chaos down there, time cannot stay calm and steady. Time must churn too. What does churning time even mean? Picture the normal flow of time as a river, moving smoothly in one direction. Now imagine that river hitting rapids so violent that the water sprays in every direction at once, some of it flying backward, some sideways, some standing still. In that chaos, the simple question, which way is downstream, stops having a clear answer. At the Planck scale, some scientists think time behaves like those rapids. The clean arrow from past to future dissolves into a mess where before and after blur together. Take it further. Remember the permanent blur, the rule that you can never pin down everything at once. That blur applies to time as well. Down at the smallest scale, the very order of events may go fuzzy. Did this happen before that or after? The universe might refuse to give a sharp answer. Two events could exist in a haze where neither one clearly comes first. The neat line of time smears into a cloud. Some of the boldest thinkers push this to the edge. They wonder if time is not a basic ingredient of the universe at all. In their idea, time is not woven into the deepest layer of reality. Instead, time appears later, emerging from something more fundamental underneath. The way temperature appears from countless atoms jiggling. A single atom has no temperature. Temperature only shows up when trillions of atoms move together. These scientists think time might work the same way. At the smallest scale, there is no time. Time only emerges when enough tiny pieces come together at larger sizes. Let that sink into place with a comparison. Watch a huge crowd in a stadium do the wave, standing and sitting in sequence so a ripple seems to travel around the stands. The wave looks real. It moves. It flows. But no single person is the wave. The wave only exists because thousands of people act together. If time is like that wave, then at the level of a single Planck-sized grain, there is no flow of time at all. Time is a pattern that only appears when the grains join into a crowd. Now the truth, plainly. This is among the most speculative ideas in all of physics. Nobody has confirmed that time breaks down or emerges from something deeper. It is a frontier, a place where the smartest people admit they are mostly guessing. The mystery of time at the smallest scale is wide open. But this whole strange journey, the foam, the grains, the flickering time, all of it grew from trying to force gravity and the quantum world to get along. And there is another giant theory that tackles the same challenge from a completely different direction. It says everything, all of it, is made of something you would never expect. Tiny vibrating strings. Everything we have explored so far pictures the smallest pieces of reality as dots, grains or bubbles, little specks. But one of the most famous theories in all of science says the true building blocks are not specks at all. They are strings. Tiny, vibrating strings, and you are made of them right now. This is string theory, and its central idea is oddly beautiful. Take any tiny building block of matter, one of the little specks deep inside an atom. Zoom in on it, closer than anyone can actually see. String theory says that if you could look closely enough, that speck would not be a dot. It would be a tiny loop or line of pure energy, a string, wiggling and vibrating like a plucked guitar string. Here is the part that makes people fall in love with the idea. Every kind of particle in the universe, every different building block, would be made of the same kind of string. What makes them different is how the string vibrates. Pluck a guitar string one way, and you get a low note. Pluck it another way, and you get a high note. Same string, different sounds. String theory says the universe works like that. One kind of string, vibrating one way, becomes one type of particle. Vibrating another way, it becomes a completely different type. Everything you see, every speck of matter, every beam of light, is a different note played on the same kind of tiny string. Sit with that picture, because it is stunning. It means the whole universe is a kind of music. Every atom in your body, every star in the sky, every ray of light from the sun, all of it is made of tiny strings, each one humming its own note. Reality becomes a vast, silent symphony, played on strings too small to ever see, and the different notes are the different things that exist. Here is why this excites so many physicists. Remember the Great Clash, gravity fighting the quantum world, spitting out infinities every time you go too small. String theory offers a way to calm that fight. When the smallest things are tiny strings instead of zero-sized dots, they are not infinitely small. They have a size. and that size stops the infinities from ever appearing, much like the loops and grains did in the other theory, but through a completely different door. Even better, when scientists worked out the math of string theory, something remarkable fell out on its own. The equations naturally produced a description of gravity without anyone forcing it in. A theory built to describe tiny particles handed back gravity for free. To many physicists, that felt like a powerful clue that strings might be touching something true. Now the honest part, and it is a big one, string theory is not confirmed. No experiment has ever seen a string, and the strings would be so small that seeing one directly may be impossible forever. Some scientists champion string theory as our best hope for uniting all of physics. Others criticize it for being nearly impossible to test. The debate is fierce and unresolved. But there is one detail about these strings that connects straight back to everything we have chased: their size. Because when you ask how big these tiny strings actually are, the answer lands on a number we have met again and again, the number that keeps appearing at the very bottom of reality. How big is one of these vibrating strings? This is where string theory reaches down and shakes hands with everything we have explored. Because the answer is not some random size. The strings are almost exactly the size of the Planck length, the smallest distance we keep crashing into from every direction. Think about how strange that is. We started this journey by finding a mysterious wall at the bottom of space, the Planck length, discovered from math about light and heat. Then loop quantum gravity showed up and said space is woven from loops about that same size. Now string theory arrives from a totally different path, built on totally different ideas, and it says the fundamental strings are also about that same size. Different theories, different tools, different scientists, all pointing at the same tiny number. That is the kind of clue that makes physicists sit up. When wildly different roads all lead to the same place, it hints that the place is real. The Planck length keeps showing up because something genuinely important is happening there, no matter which theory you use to look. So picture it now. A string vibrating at the Planck length is unthinkably small. Remember the comparison from before, where you blow up an atom to the size of the whole visible universe, and the Planck length is still just a football field inside it. A string is around that size. It is so far below an atom that calling it small does the word an injustice. And yet, in this theory, these are the threads that everything is stitched from. The smallest things in existence, humming at the very floor of reality. Here is a comparison to feel the scale of the idea. Imagine the universe as the largest orchestra ever assembled, so vast it contains every star and galaxy. Now imagine that every single instrument in that orchestra is a string smaller than the smallest thing science can measure, each one playing a note that becomes a particle. The music of that orchestra is not sound, the music is matter itself. The music is you. This also ties back to why strings might solve the Great Clash. A dot has no size and zero-sized things create infinities when gravity and the quantum world collide. But a string has a smallest size right at the Planck length, and that size acts like a shield. It smooths out the violent clash, blurring the sharpest point where the theories broke. The Planck length, once a wall that stopped us cold, becomes the very thing that saves the math. Now the reminder, because it stays true, all of this is theory, unconfirmed. Strings this small can probably never be seen directly, and that is exactly why so many scientists worry the whole idea may be impossible to fully prove. It is a beautiful guess, a powerful guess, backed by gorgeous math, but a guess all the same. The strings might be real, or the truth might be something no one has imagined yet. Still, string theory has one more shock hidden inside it, and it may be the most bizarre claim of all. To make the math work, the strings need room to vibrate, and they need far more room than the world seems to offer. String theory says our universe must be hiding extra dimensions, secret directions of space, curled up so small that we have never noticed them. And where they hide is stranger than anywhere we have been. You know, 3 directions, left and right, forward and back, up and down. Every place you have ever been, every step you have ever taken fits inside those 3. They are the directions of space, and they feel like all there is. String theory says you are wrong. For the tiny strings to vibrate in all the ways the math demands, 3 directions are not enough. The strings need more room, more directions to wiggle in, and when scientists count how many the equations require, the answer is shocking. String theory says the universe has extra dimensions of space, hidden ones beyond the three we know. Right away, a fair question jumps up. If there are more directions, where are they? You cannot point to them. You cannot walk into them. You have never bumped into a fourth way to move. So how can they possibly be real? String theory has a clever answer. The extra dimensions are curled up. They are wound so tightly, into loops so unbelievably small, that you could never notice them, and their size, once again, is right around the Planck length. They are folded away at the very bottom of reality, hidden in the same place all our mysteries keep hiding. Here is a comparison that makes it click. Picture a garden hose from far away. It looks like a thin line, a one-dimensional thread you could only move along in one direction, back and forth. But walk up close, and you see the truth. The hose has another dimension wrapped around it. A tiny ant on the surface could crawl not just along the hose but also around it, looping the short way. From far off, that curled direction was invisible. Up close, it was there all along. String theory says our universe is like that hose. The three big directions are easy to see, stretched out huge, but at every single point in space, tucked into every spot, there are extra directions curled up too small to ever spot. You're surrounded by them right now. They thread through the air in front of your face, through your own body, wound up at the Planck scale, silent and unseen. Sit with how wild that is. It means the space you live in might be far richer than it looks. Not a simple room with three directions, but a deep folded structure with secret dimensions hidden in every corner, packed away beneath the smallest size you can imagine. And here is why scientists care, beyond the strangeness. In string theory, the exact way those extra dimensions are curled up decides everything. The shape of the folds controls how the strings vibrate. And how the strings vibrate decides what particles exist, what forces exist, what kind of universe you get. Change the folding, and you change reality itself. The hidden dimensions might be the secret blueprint behind all the laws of physics. Now, the honest truth, no one has ever detected an extra dimension. Scientists have searched, smashing particles together in giant machines, hoping to knock something loose into a hidden direction. So far, nothing. The extra dimensions remain a bold prediction, unconfirmed, possibly untestable, and some physicists doubt they exist at all. But the idea that reality has hidden layers, folded away at the smallest scale, opens a door to something even more mind-bending. What if the world around you is not as solid or as real as it seems? What if everything you see is a kind of projection, painted onto a surface far away? Get ready, because this next idea is the strangest one yet, and serious physicists actually believe it might be true. It is called the holographic principle, and it says something that sounds impossible. It says everything happening in a chunk of space, all of it, every atom, every event, all the depth and volume, could be fully described by information written only on the surface around that chunk. The inside is captured by the outside. The three-dimensional world you feel might be like a projection, painted on a distant two-dimensional wall. Start with something familiar. You have seen a hologram, maybe on a credit card or a fancy sticker. It is a flat surface, totally flat with no real depth, but tilt it in the light, and a three-dimensional image seems to pop out floating, with front and back and sides. All that depth is an illusion, encoded in a flat sheet. The flat surface holds every detail needed to build the three-dimensional picture. The holographic principle says the universe might work the same way. The rich, deep, three-dimensional world you move through could be encoded on a flat surface somewhere, the way a hologram's depth is encoded on its flat film. Everything with volume might really be information stored on a boundary with no volume at all. Feel how deeply strange this is. Right now you sense space all around you. The room has width, height, depth. You can walk into it. It feels utterly solid and real. The holographic principle whispers that all of this could be a projection, that the true story is written on a surface you cannot see, and the space you feel is the image that surface creates. Here is a comparison to hold on to. Think of a movie in a theatre. The screen is flat, just a two-dimensional sheet on the wall. But the story it shows has deep spaces, tall buildings, wide landscapes, characters walking toward you and away. All that world lives on a flat screen. The holographic principle suggests our universe might be like that, a deep world encoded on a flat surface. so convincing that we mistake the projection for the real thing. Now you might expect me to say this is just a wild guess. But here is the twist. This idea did not come from dreamers. It came from cold, careful math, from some of the most respected physicists alive, and it came out of studying the most extreme objects in the universe, black holes. When scientists worked out the deep rules of black holes, the holographic principle fell out almost by force. The math practically demanded it. That is what makes it so haunting. It is strange beyond belief, yet it rests on solid reasoning that keeps checking out. Many top physicists now take it seriously as a possible truth about reality, though it is not fully confirmed, and the debate over what it really means goes on. So how did black holes, of all things, reveal that our whole world might be a projection? The answer takes us back to the smaller scale, and to a discovery that shows information itself comes in tiny pieces, each one about the size of the Planck length. To understand why the universe might be a hologram, we have to look at a black hole in a way you've probably never heard. Because black holes hold a secret about information, and that secret points straight down to the Planck length. Start with a strange question. How much stuff can you cram into a black hole? How much information can it hold? You might guess the answer depends on how big the inside is, the volume, the room within. That would make sense. A bigger box holds more. But black holes break that rule, and the way they break it change physics forever. Scientists discovered that the amount of information a black hole can hold does not depend on its volume at all. It depends on its surface. The area of the wall around it, the boundary called the event horizon. Double the surface, and you double how much the black hole can store. The inside volume does not matter, only the skin does. This was a bombshell. Everywhere else in life, capacity depends on volume. A bigger room holds more furniture. A bigger tank holds more water. But a black hole, the most extreme object in the cosmos, stores its information on its surface, like writing on the outside of a sealed box instead of packing things inside. That single fact is the seed of the whole holographic idea. If the deepest objects in the universe store their information on surfaces, maybe everything does. Now here comes the part that ties it to the smaller scale. When scientists worked out exactly how much information a black hole's surface can hold, they found the surface is divided into tiny squares, and each square is about the size of the Planck length across. The surface of a black hole is like a checkerboard, made of the smallest possible tiles, and each tile carries a single scrap of information. Picture it clearly. Take the boundary of a black hole and cover it in a grid, the way graph paper is covered in squares. Make each square one Planck length on each side, the smallest square that can exist. Count all those squares, and that count tells you exactly how much the black hole can hold. The information is not spread smoothly, it is chopped into smallest pieces, one per tiny tile. Here is a comparison to make it stick. Think of a giant screen made of the tiniest lights, each light holding one dot of a picture. The screen can only show as much detail as it has lights. A black hole is like that, except its lights are Planck-sized squares, and they cover its surface, each one storing the smallest possible piece of information. This is one of the deepest results in modern physics, and the reasoning behind it is widely respected, built by combining gravity, the quantum world, and the science of heat. It is as close to solid as such a wild idea can get, though the full meaning is still argued over, and it leads to a conclusion that stuns everyone who hears it. If information comes in Planck-sized squares, then information itself is grainy, chopped into smallest units. There is a tiniest possible piece of information in the universe, a single yes or no, and it fits on a patch of space right at the Planck length. Let's follow that stunning idea all the way to its end, because it may be the deepest truth we have touched yet. If a black hole stores information in Planck-sized squares, then the universe has a smallest possible piece of information. And that changes what reality is made of. First, what is a piece of information? At the bottom, information comes down to a single choice. Yes or no. On or off. 1 or 0. Scientists call this smallest scrap a bit. Every photo on your phone, every song, every message is built from billions of these tiny yes or no answers, strung together. A bit is the atom of information, the smallest meaningful unit there is. Now here is the astonishing claim. The discovery about black holes says that a single bit of information takes up a single patch of space, about one Planck length across. You cannot pack information tighter than that. 1 bit per Planck size square is the absolute limit the universe allows. Try to squeeze in more, and space itself collapses into a black hole, hiding the extra away. The Planck scale is not just the smallest length, it is the smallest place you can store a single yes or no. Feel what this means. It suggests the universe has a maximum amount of detail. There is a finest possible resolution to reality, a sharpest the picture can ever get, set by the size of these tiny patches. The world cannot hold infinite detail. It is limited, pixel by pixel, bit by bit, down at the Planck length. This is where a breathtaking possibility opens up. If space stores information in smallest bits, then maybe, deep down, the universe is made of information. Not made of tiny balls of matter, not made of little strings, made of pure information, of countless yes and no answers, written across space at the Planck scale, and everything you see, all the matter and light and motion, is what that information looks like from the inside. Some of the boldest thinkers in science suspect exactly this. They wonder if reality is, at its core, something like a vast computation, a universe of bits updating step by step, and the physical world we experience is the result. In this view, a star, a tree, your own beating heart. All of it is information doing its dance, written on the smallest patches space allows. Here is a comparison to carry with you. Think of the richest, most detailed video game world imaginable. So real you could walk through it. Underneath all that beauty, it is just information, just bits in a machine, ones and zeros, arranged to look like a world. Some scientists think our universe might share that deep nature, built from bits at the Planck scale, so numerous and so fine that the whole cosmos feels completely solid and real. Now, honesty. The idea that the universe is fundamentally information is not proven. The black hole result is solid, and the 1 bit per patch limit is widely accepted. But the leap to saying reality is truly made of information is a bold interpretation, not a confirmed fact. It is a frontier, exciting, and unfinished. Yet even setting that aside, we keep circling one strange truth. Empty space is doing far more than we ever thought. It stores information, it boils with foam, and it turns out it is also packed with a hidden energy, a secret power humming inside the emptiness itself. Look at the empty air in front of you. There seems to be nothing there. No stuff, no matter, just a gap, a bit of blank space between you and the far wall. It feels like the definition of nothing. But at the smallest scale, that nothing is a lie. Empty space is secretly bursting with energy. We already met the reason. Remember the permanent blur, the rule that things can never fully hold still, and that energy is allowed to flicker for tiny moments. That flickering never stops. Even in the emptiest spot imaginable, with all the matter removed, all the light gone, the energy keeps trembling. Tiny sparks flash in and out, popping up and vanishing faster than any clock could catch. Empty space is alive with this restless buzzing. Scientists have a name for this hidden energy of empty space. They call it vacuum energy. And here is the strange part, it is not a wild guess. This energy is real, tested, and confirmed. We have measured its effects in the lab. Empty space genuinely carries energy, humming away in every gap, even in the deepest void far from any star. Picture it this way. You think of a quiet, empty room as still and silent. But down at the smallest scale, that room is a fireworks show. Tiny flashes are going off everywhere constantly, sparks of energy flickering into being and then gone, trillions upon trillions of them, filling every speck of the room. The stillness you see is an illusion, a calm surface stretched over a frenzy too small and too fast to notice. Now stretch your imagination. This buzzing fills all of space, everywhere, all the time. The gap between your hand and this screen, the huge emptiness between Earth and the moon, the vast dark between stars, all of it packed with this restless vacuum energy, quietly seething at a scale far below sight. Here is why scientists find this so important. If empty space carries energy, then empty space is not just a passive stage where things happen. It is an active player. Its hidden energy can push and pull on the universe itself. In fact, many scientists think this vacuum energy might be behind one of the biggest mysteries in all of science, the strange force that is making the entire universe expand faster and faster, stretching the cosmos apart. The energy of nothing might be shaping the fate of everything. Let that land. The emptiest thing you can imagine, pure empty space, might be steering the future of the whole universe, driving galaxies apart, all because it is secretly full of a trembling energy born at the smallest scale. This part rests on solid ground. The buzzing of empty space is confirmed by careful experiments, and it flows directly from the quantum rules we trust. Scientists are confident the energy is there, but when they try to calculate exactly how much energy empty space should hold, something goes horribly wrong. The answer they get is one of the most catastrophic failures in the history of science, a mistake so enormous it should never happen. And that failure is a giant flashing clue that we are still missing something huge about the smallest scale. Before we face that failure though, there is a beautiful experiment that proves the energy of nothing is real. 2 metal plates and a push that comes from pure emptiness. Before we watch 2 plates get pushed by nothing, we need one more strange fact about the energy hidden in empty space. It never turns off. No matter how cold you make things, no matter how still, the buzzing keeps going. And that fact breaks a rule almost everyone believes. Here is the rule people expect. Cold makes things slow down. Heat is motion, tiny jiggling of particles, and the colder something gets, the less it jiggles. So you would think that if you cooled something all the way down, to the coldest temperature possible, all motion would stop completely. Perfect stillness. Everything frozen solid, not a wiggle left. There is even a name for that coldest possible temperature. Scientists call it absolute zero, the bottom of cold, the point where you cannot get any colder. And for a long time, people assumed that at absolute zero, everything would be perfectly, totally still. But the quantum world says no. Even at absolute zero, even at the coldest cold that can exist, the tiny building blocks of everything still refuse to hold still. They keep a little jiggle, a leftover trembling that can never be removed. Scientists call this leftover motion 0-point energy, because it is the energy that remains at the 0 point of cold when everything else has been taken away. Why can it never stop? Because of the permanent blur we met earlier. Remember, you can never pin down both where a tiny thing is and how fast it moves. If a particle froze completely still, you would know both things perfectly. Its position would be exact, and its speed would be exactly 0. The blur forbids that. Nature refuses to allow perfect stillness, because perfect stillness would mean perfect knowledge, and the blur says that is impossible. So the trembling must go on forever, as the price of the blur. Sit with how deep that is. The universe cannot allow anything to be perfectly still. Total stillness is banned by the deepest laws of reality. There is always a shiver, always a hum, always a little motion left, down at the smallest scale, no matter what you do. Here is a comparison to feel it. Imagine a swing that can never stop swinging. You try everything to still it. You hold it, you slow it, you cool the whole playground to the coldest temperature imaginable, and still, when you let go, the swing keeps trembling, back and forth, ever so slightly because the rules of the universe simply will not let it rest. Every tiny piece of everything is like that swing, shivering forever, unable to fully stop. This trembling is not just a fun idea, it is confirmed, real, and important. 0-point energy shapes how materials behave at very cold temperatures. It keeps certain substances liquid when they should freeze. Scientists work with its effects in real laboratories. The never-ending jiggle of the quantum world is a proven fact, not a guess. And this restless energy, the buzzing that never stops even at absolute 0, does something you can actually feel the fingerprint of. If empty space is truly full of this trembling energy, then it should be able to push on real objects. It should exert a force, a gentle shove that comes from nowhere but the emptiness itself. Scientists found a way to catch that shove, and they did it with nothing more than 2 flat metal plates held incredibly close together. Here is one of the most beautiful experiments in all of physics, and it proves that the energy of empty space is real. It uses 2 simple metal plates and a push that comes from pure nothing. Set up the experiment in your mind. Take 2 flat metal plates, smooth and clean. Hold them facing each other, parallel, like 2 walls. Now bring them very close together. closer than a hair's width, almost touching but not quite. Around them and between them is only empty space. No springs, no magnets, no glue, nothing connecting them. Just two plates and the vacuum. Common sense says nothing should happen. Empty space is empty. Two plates sitting in nothing should just stay put, feeling no push at all. But that is not what happens. Instead, the two plates feel a gentle force pulling them together. Left alone, they drift toward each other, pushed by the emptiness itself. This is real. It has been measured in laboratories. Scientists call it the Casimir effect, and it is confirmed beyond doubt. Where does the push come from? From the buzzing energy of empty space, the restless flickering we have been chasing. Here is the clever part. Empty space is full of tiny energy waves of all sizes, flickering in every gap. Out in the open, beyond the plates, waves of every size can fit. But squeeze into the tiny gap between the plates, and only certain sizes of waves can fit in there, the way only certain notes fit inside a small pipe. Some waves get crowded out of the gap, so there are more energy waves outside the plates than inside the gap between them. More buzzing pushing in from the outside, less pushing back from the inside. The result is a squeeze. The greater energy outside shoves the plates together, pressing them closer, all because the empty space between them holds a little less buzz than the space around them. Let that sink into place. Two solid metal plates are moved by nothing but empty space. The push has no source you could point to, no motor, no field you added. It comes purely from the difference in how much the vacuum can buzz inside the gap versus outside it. Nothing is doing the pushing, and yet the plates move. Here is a comparison to hold on to. Imagine two ships floating side by side on a choppy sea, with waves crashing all around them. Out in the open water, big waves hit the far sides of both ships. But in the narrow gap between them, the big waves cannot fit, so the water there is calmer. The stronger waves on the outside push the ships together, drifting them into each other across the quiet gap. The Casimir effect works much the same way, except the sea is empty space, and the waves are the buzzing energy of the vacuum. This experiment is huge, because it takes the energy of nothing and makes it do something you can measure with real tools. It proves empty space is not empty. The vacuum has power, and that power moves solid metal. Scientists trust this completely. It has been tested many times, and it works every time. So we know empty space carries energy. We have felt its push. But when scientists try to calculate exactly how much energy the vacuum holds, they run headfirst into a disaster. The single worst prediction ever made in the history of science. Scientists know empty space holds energy. They have measured its push with the plates, so the next step seems obvious. Sit down, do the math, and calculate exactly how much energy is packed into the vacuum. Add up all that buzzing at the smallest scale and get a number. They did the calculation, and what came out is the single most embarrassing failure in the history of physics. Here is the problem. When you add up all the flickering energy of empty space, counting every tiny buzz down toward the Planck scale, the total grows and grows. The smaller the flickers you include, the more energy you pile up. By the time you reach the Planck length, the energy has swollen to a staggering, monstrous amount. The math predicts that every tiny speck of empty space should be crammed with a colossal crushing energy. Then scientists looked at the real universe to check. They measured how much energy empty space actually carries by watching how the cosmos expands. And the real number is almost nothing. A tiny whisper of energy, unbelievably gentle, barely there at all. Now compare the two, the prediction from the math and the measurement from the real universe. They should match. Instead, the predicted number is bigger than the real one by an amount so vast it breaks the mind. Write the two numbers side by side, and the difference has more zeros than you could fit on a page. Some say it is the worst mismatch between prediction and reality in all of science, off by a factor so enormous that no ordinary word can describe it. Think about what that means. Our best theories, the ones that get almost everything else right to incredible precision, predict that empty space should hold a mountain of energy. The universe says it holds a feather. The gap between mountain and feather is so huge, it is almost funny. Except it is deadly serious, because it means we're missing something enormous about how reality works at the smallest scale. Here is a comparison to feel the size of the failure. Imagine you calculate how much a small bag of groceries should weigh, and your math says it should weigh more than every star in every galaxy combined. Then you put the bag on a scale, and it weighs a few pounds just like it should. Your method was not a little off. It was so wrong that something must be deeply broken in how you were thinking. That is where physics stands with the energy of empty space. Scientists call this the worst prediction problem, and it is completely real, fully admitted, one of the great unsolved puzzles hanging over all of physics. Nobody has fixed it. The best minds alive have thrown everything they have at it, and the mismatch stubbornly remains. This is not a small crack. It is a giant warning sign flashing at the smallest scale, telling us our understanding is incomplete, and that is strangely thrilling. A failure this big means there is a huge discovery waiting, a missing piece so important it could reshape all of physics. Somewhere down at the Planck scale, something is quietly cancelling that mountain of energy almost perfectly, and we have no idea what. The mystery of the vacuum runs deep. But the smallest scale hides an even wilder possibility. What if space down there does not just buzz and boil, but actually tears? What if the fabric of reality can rip wide open? We talk about the fabric of space, the sheet that everything sits on, but a fabric can tear, a sheet can rip. So here is a question that sounds impossible. Can space itself rip open? Can the fabric of reality tear apart at the smallest scale? For everyday space, the answer seems to be no. The space around you is smooth and calm and whole. You can wave your hand through it, cut it, punch it, and nothing tears. Space just flows around whatever you do, seamless and unbroken. At the sizes we live in, the fabric of reality is incredibly tough, but go down toward the Planck length, into the churning foam, and everything changes. Remember the picture of quantum foam, space boiling and twisting, ripping open into tiny black holes and pinching shut again. If that picture is right, then space at the smallest scale is tearing constantly. Little rips open up, then heal, tiny holes form, then vanish. The smooth fabric we trust is really a frenzy of ripping and mending, happening faster than any clock could follow. This means the wholeness of space might be a large-scale illusion. Up here where we live, space looks perfectly solid and unbroken. But that could be like looking at a calm lake from far away. The surface seems like a flawless mirror. Get close, and you see it is trembling with tiny ripples and breaks. Space might be the same, smooth from a distance, torn to shreds at the bottom. Here is a comparison to hold on to. Think of a piece of paper. Whole and flat. It seems solid, impossible to see through. But look at it under a powerful microscope, and you find it is full of gaps. Fibers crossing with holes between them, a rough and broken landscape. The paper only looked smooth because you were too far away to see the holes. Space might hide the same secret, riddled with tears at a scale far below sight. Now why does any of this matter beyond being strange? Because if space can tear, it changes what is possible. A tear in space might, in wild theory, connect one place to another. Two rips could join, forming a shortcut, a tunnel through the fabric of reality. And in the boiling foam, these tears and tunnels might be forming and collapsing all the time, everywhere, flickering through the emptiness. Be careful here, because we are deep in theory now. Nobody has ever seen space tear. Nobody has caught a rip in the fabric of reality. This all comes from pushing our equations down to the Planck scale, where they hint at ripping and reforming, but where we cannot actually look to check. It is a serious idea, taken seriously by serious scientists, but it is unconfirmed, a possibility rather than a proven fact. Still, the idea refuses to go away, because the math keeps suggesting it. When gravity and the quantum world are forced together at the smallest scale, space stops behaving like a calm, unbreakable sheet. It starts to look fragile, violent, alive, with tearing. And those flickering tears lead to one of the most famous and mind-bending ideas in all of science. Tunnels through space, connecting distant points, appearing and vanishing inside the foam. Bridges through reality itself, born and destroyed at the smallest scale. The tears in space at the smallest scale lead to an idea straight out of the wildest dreams of science. Tunnels through reality, shortcuts that connect one place to another, punched right through the fabric of space. You may have heard their name before, wormholes. Here is the idea in simple terms. Normally, to get from one point to another, you travel the distance between them. Space stretches between the two spots, and you have to cross it. But a wormhole would be a tunnel that connects two separate points directly, skipping the space in between. Enter one end, come out the other, having crossed a gap that might otherwise be huge, all through a shortcut folded through reality. Picture it with a classic comparison. Imagine space is a flat sheet of paper, and two dots are drawn far apart on it. Normally, to get from one dot to the other, you slide across the paper, covering the whole distance. But now fold the paper so the two dots touch. Punch a hole where they meet and you have a tunnel. Now you can hop straight from one dot to the other, skipping all the paper in between. That tunnel is a wormhole, a bridge that connects distant points by folding space itself. Now bring this down to the smallest scale, into the quantum foam. Some scientists think that in the boiling froth at the Planck length, tiny wormholes are forming and collapsing all the time. The foam tears open, two rips connect, a microscopic tunnel appears, and then it pinches shut and vanishes, all faster than any clock could catch. In this picture, the emptiness in front of your face is threaded with countless tiny tunnels, flickering in and out of existence, billions upon billions of them, weaving through the smallest scale of space. Sit with that image. The calm, empty air you see might secretly be a churning tangle of tunnels, opening and closing through reality, connecting tiny points across space, born and destroyed in the blink of an impossibly fast eye. The bottom of reality would be less like a smooth floor and more like a frenzied web of shortcuts, constantly rewiring itself. Here is the honest truth, and it is important. No one has ever seen a wormhole. Not a big one, not a tiny one, not any. They come out of the equations when you push gravity to its limits, and they are allowed by the math in theory. But whether real wormholes exist, whether the foam is truly full of them, remains completely unproven. It is one of the most speculative ideas in physics, exciting and unconfirmed, living at the edge of what we can even think about clearly. Why do scientists bother with such a wild idea? Because these tiny tunnels might solve deep puzzles. They might explain how distant parts of the universe are connected. They might link to the strange energy of empty space. And they connect to an idea so bold it may be the strangest twist in this entire journey. Because some scientists now wonder if these tunnels, these connections through the foam, might be doing something almost unbelievable. They might be the very thing that holds space together, the threads that stitch reality into one connected whole, and the needle doing the stitching might be one of the deepest mysteries in all of physics. Here comes one of the most beautiful and mind-bending ideas in modern physics. Some scientists now think that space itself might be held together by a strange, invisible connection between tiny pieces, and that connection has a name that sounds like magic, though it is completely real. Entanglement. First, what is entanglement? It is one of the strangest facts in the quantum world, and it is confirmed, tested, proven true. When two tiny particles become entangled, they form a deep link. Measure one, and you instantly know something about the other, no matter how far apart they are. Two specks connected by an invisible thread, sharing a single fate across any distance. Scientists have tested this again and again, and it always holds. Entanglement is real. For a long time, entanglement seemed like just a bizarre quirk of tiny particles, a strange trick nature plays. But recently, some of the boldest physicists alive started to wonder if it might be something far bigger. What if entanglement is not just a quirk? What if it is the glue that holds space itself together? Here is the astonishing idea. Picture space as being made of countless tiny pieces, the grains we have talked about. What connects one grain to its neighbour? What makes them stick together into smooth, connected space instead of a scattered dust of unrelated specks? The answer, some scientists propose, is entanglement. Neighbouring pieces of space are entangled with each other, linked by that invisible quantum thread, and those links are what weave the pieces into one connected whole. Feel how deep this goes. In this picture, entanglement is the stitching. It is the thread running between every tiny piece of space, sewing them together into the smooth fabric you move through. Cut the entanglement, snip the threads, and space would fall apart, unraveling into disconnected scraps. The very connectedness of space, the fact that here smoothly leads to there, might come from these quantum links at the smallest scale. Here is a comparison to hold on to. Think of a sweater. It looks like one solid, connected piece of fabric, but it is really made of a single thread, looped and linked together over and over. The connections between the loops are what make it a sweater instead of a pile of yarn. Pull the right thread, and the whole thing unravels. Some scientists think space is like that sweater, and entanglement is the thread. The linking is what makes space hold together as one smooth thing. This idea has been gaining real strength. Serious physicists have found deep math hinting that space and entanglement are tied together, that the structure of space might grow directly out of the pattern of quantum links between its pieces. It is one of the hottest frontiers in all of physics, buzzing with excitement. But stay honest. This is a frontier idea, not a settled fact. Nobody has proven that entanglement builds space. It is a bold, thrilling proposal, backed by suggestive math, still being explored and argued over. It might turn out to be the key to everything, or it might be a beautiful clue pointing towards something even deeper. And that word, deeper, opens the biggest question of all. If space is stitched from entanglement, then space might not be a basic ingredient of reality at all. Space might be something that grows, something built, something that emerges from a deeper layer where space does not even exist. Get ready for the most radical idea in this entire journey. Some of the smartest physicists alive now suspect that space is not a basic ingredient of the universe at all. Space might not be fundamental. It might be something that emerges, that grows out of something deeper, a layer of reality where space does not even exist. This flips everything upside down. For all of history, space seemed like the ultimate stage, the container that everything else happens inside. You put the universe in space. Space came first and stuff filled it. That felt obvious, unquestionable, the bedrock of reality. Now a growing group of scientists wonders if space is not the bedrock after all, but something that appears on top of a deeper foundation, the way a picture appears on top of pixels. What does it mean for space to emerge? Think about temperature. A single atom has no temperature. Ask how hot one lonely atom is, and the question makes no sense. But gather trillions of atoms together, let them jiggle and bump, and suddenly temperature appears. Heat emerges from the group even though no single piece has it. Temperature is real, but it is not fundamental. It grows out of something deeper, the motion of countless atoms. Some scientists think space works the same way. At the deepest level, there might be no space, just a web of connections, a tangle of quantum links with no distances and no directions. And out of that web, when enough pieces link together in the right pattern, space emerges, the way temperature emerges from atoms. Distance, direction, nearness, all of it would be a large-scale pattern, not a basic truth. Space would be real, but built, not fundamental. Sit with how strange this is. It means the deepest layer of reality might have no space at all. No here, no there, no far, no near. Just pure connection, a network of links, and everything you experience as space. The room around you, the distance to the stars, the gap between your hands, all of it would be a pattern woven from those links, appearing only when you zoom out far enough to see the crowd, instead of the individuals. Here is a comparison to carry with you. Think of a photo on a screen showing a wide landscape with deep distance, mountains far away, a path stretching toward the horizon. All that space and distance looks real. But zoom in, and it is just pixels, tiny dots with no landscape inside them, no real distance at all. The space in the picture is not in any single pixel. It emerges from the whole pattern of pixels together. The universe might be like that, with real space emerging from a deeper pattern that has no space inside it. Now the honest truth. This is among the most speculative frontiers in all of science, unproven and hotly debated. But it is not idle dreaming. It comes from serious math, from studying black holes and entanglement and the holographic idea, all pointing the same strange direction, hinting that space grows out of something deeper. If space really does emerge, then the deepest question becomes clear. What is that deeper layer made of? If not space, then what? And one bold answer says the foundation of reality is not made of things at all, but of pure events, tiny happenings, connected in a web that builds the universe from the ground up. If space is not fundamental, then what is? One bold idea gives a startling answer. The universe, at its deepest level, is not made of things at all. It is made of events, tiny happenings, little moments where something occurs, linked together into a vast web, and out of that web, space and time are built. This idea is called causal set theory, and its picture is stark and beautiful. Forget space as a smooth sheet. Forget grains and strings and loops. Go deeper. At the very bottom, imagine reality is just a huge collection of separate events, like tiny points of happening scattered through nothing. Each event is a single moment, a smallest possible occurrence, and these events are connected by one simple relationship. Which one came before which? That is the whole foundation, just events, and the order between them. This happened before that. That happened before this other thing. A vast web of befores and afters, linking countless tiny events into a network. And astonishingly, from nothing but that web of order, both space and time are supposed to grow. The universe is built from the pattern of what leads to what. Feel how stripped down this is. There is no smooth space to start with. No flowing time, no stage, no container, nothing but a scatter of events and the links of before and after between them. Everything else, all of space, all of time, the whole rich universe, emerges from that bare web of ordered happenings. It is like building reality from the simplest possible ingredient, pure cause and effect, one event leading to the next. Here is a comparison to hold on to. Think of a family tree. It is just people and links, showing who came before whom, who led to whom. From that simple pattern of befores and afters, a whole rich history emerges, generations, branches, a vast connected structure. Causal set theory says the universe is like a family tree of events, where each happening leads to the next, and the entire structure of space and time grows out of that web of connections. Why do scientists take this seriously? Because it naturally makes space and time grainy, built from smallest events, which dodges the infinities that plague other approaches, and it starts from something wonderfully simple, just events and order, rather than assuming smooth space from the beginning. Some physicists find that simplicity deeply appealing, a clean foundation for everything. Now the honest reminder, causal set theory is one idea among several, all competing to describe the deepest layer of reality, and none of them is confirmed. Loop quantum gravity, string theory, causal sets, emergent space from entanglement, these are rival visions, each capturing something, each unproven. Scientists genuinely do not yet know which, if any, is right. This is the raw frontier of physics, where honest researchers admit the answer is still unknown, and that brings us to the hardest wall of all. We have explored foam and grains, strings and loops, holograms and events, wild ideas, beautiful math, competing visions of the bottom of reality. But every single one runs into the same brutal problem. We cannot look. We cannot check. The smallest scale hides behind a trap so perfect that seeing it may be impossible forever. We have travelled to the bottom of reality and met wonders. Boiling foam, grains of space, vibrating strings, hidden dimensions, holograms and wormholes, beautiful competing visions of what space is made of at the smallest scale. But now we face the cruelest truth of the whole journey. We may never be able to check which one is right, because the smallest scale is protected by a trap we cannot beat. We met this trap early on, and now we understand its full weight. To see something tiny, you must hit it with energy. The tinier the target, the more energy you need. And to see all the way down to the Planck length, You would need so much energy crammed into so small a spot that it collapses into a tiny black hole, swallowing the very thing you wanted to see. Every attempt to look ends the same way. The door slams shut. The answer vanishes behind a wall no experiment can cross. This is not a problem of weak tools or limited money. It is not something a better machine will fix next century. The trap is built into the laws of nature themselves. The act of looking closely enough destroys what you are looking at every single time, no matter how clever you are. The Planck scale defends itself, using the deepest rules of physics as its shield. Think about how strange and frustrating this is. For most mysteries in science, the path is clear. Build a better telescope, a bigger microscope, a stronger machine, and eventually you see the answer. Curiosity plus effort equals discovery. But the smallest scale breaks that promise. Here, more effort makes the wall stronger, not weaker. Push harder, and it seals tighter. The universe has hidden its deepest secret in the one place we can never directly reach. To feel how large this trap is, picture the machine you would need. To probe the Planck scale directly, scientists estimate you would need a particle collider not miles long, like the ones we have, but larger than a whole galaxy. A machine stretching across billions of stars just to reach the smallest distance. Nothing humanity could ever build, not in 1,000 years, not in 1,000,000, comes remotely close. The Planck scale sits that far beyond our reach. Here is a comparison to hold on to. Imagine a locked box, and the only way to see inside is to hit it hard enough to crack it. But this box is magic. The harder you hit it, the thicker its walls grow. A gentle tap does nothing. A mighty blow only makes it stronger. There is no swing hard enough, because your very effort feeds the box's defense. The smallest scale is a box like that, locked by its own strength. So we are left in a strange and humbling place. We have gorgeous theories about the bottom of reality, rich and detailed and competing, and we may never be able to walk up and see which one is true. The most fundamental layer of the universe might stay forever just beyond our direct sight, guarded by a trap woven into physics itself. But scientists are stubborn and clever. If they cannot look directly, they hunt for whispers, faint clues, indirect fingerprints that the smallest scale might leave on the world we can see. The chase is not over. It has just turned into detective work, searching for ghosts. If we cannot look at the smallest scale directly, then how could we ever learn the truth about it? Scientists have not given up. They have turned into detectives, hunting for faint clues, indirect fingerprints that the Planck scale might leave on the world we can actually see. They are chasing ghosts, searching for whispers of the bottom of reality. Here is the clever thinking. Even if we cannot reach the Planck length, its strange effects might leak upward, leaving tiny marks on things we can measure. If space is grainy, if it comes in smallest pieces, then maybe that graininess subtly changes how things move across the universe. Find the change, and you find proof of the grain, without ever touching it directly. It is like knowing a ghost is real not by seeing it, but by watching a door swing on its own. One hunt looks at ancient light. When light travels across the universe for billions of years, it crosses an unthinkable amount of space. If space were grainy, those countless tiny grains might trip up the light just slightly, making some colours arrive a hair earlier or later than others after such a long trip. Scientists watch light from far-off cosmic explosions, the most distant flashes we can see, checking whether different colours arrive perfectly together or slightly spread out. A tiny spread could be the fingerprint of grainy space. So far, the light arrives stubbornly together, which already rules out some ideas. Another hunt uses ripples in space itself, waves in the fabric of reality set off by giant crashes, like two black holes colliding. Scientists have built incredible machines that can feel these ripples washing over Earth. If space has a grainy structure at the bottom, it might leave a faint mark on how these ripples travel, a subtle distortion carried up from the smallest scale. Researchers comb through the ripples searching for any whisper of the Planck world hidden inside. A third hunt smashes particles together in the largest machines we have built, miles around, slamming specks together at almost the speed of light. These collisions reach deeper into smallness than anything else we can do. They are still unthinkably far from the Planck scale, but scientists watch them closely. hoping something unexpected pops out. A hint of hidden dimensions, a clue about the bottom of reality, anything that does not fit the ordinary rules. Here is a comparison to hold on to. Imagine trying to study a creature so small and shy that you can never see it. You cannot catch it. You cannot photograph it. So instead, you lay soft sand all around its home and wait. In the morning, you look for tiny footprints. You never saw the creature, but its tracks tell you it is real and hint at its shape. Scientists are laying sand all over the universe, watching for the footprints of the smallest scale. Now the honest truth, so far no clear fingerprint has been found. No experiment has caught solid proof of grainy space or the Planck world. The ghosts remain ghosts, but the hunt is real, ongoing, and growing more sensitive every year. Each new machine, each new observation, tightens the net a little more. And so we arrive at the end of our journey to the bottom of reality, standing before the deepest question of all, still unanswered, still waiting. What, in the end, is space actually made of? We have fallen all the way to the bottom of reality, past atoms, past everything, down to the Planck length, the smallest size that can exist. And now we stand before the deepest question in all of science, the one this entire journey has been building toward. What is space actually made of? Look at how far we have come. We started with a simple idea that you could zoom in forever, cutting space into smaller and smaller pieces without end. And we discovered a wall, a smallest possible size woven into the fabric of everything, where the ordinary picture of smooth, calm space completely falls apart. Below that wall we found wonders, space that boils like storm foam, ripping and healing faster than any clock, tiny black holes flickering in and out of nothing, a permanent blur that forbids perfect stillness, energy humming in the emptiest void, so much energy that our best math fails by the largest margin in the history of science, and through it all one number kept appearing, from every direction, in every theory, the Planck length, marking the floor of reality. Then we met the grand visions, the great attempts to say what space truly is. Loop quantum gravity, weaving space from tiny threads, building it up from the atoms of space themselves. String theory, claiming everything is made of tiny vibrating strings, playing the universe like a silent symphony, needing hidden dimensions curled up too small to see. The holographic principle, whispering that your whole three-dimensional world might be a projection, painted on a distant surface. And the newest, wildest ideas, that space is stitched together by entanglement, or grows out of a deeper web of pure events, and might not be fundamental at all. Here is the honest, humbling truth. We do not know which of these is right, maybe none of them. The greatest minds alive have built these beautiful competing visions, and the universe has not yet told us the answer. The trap at the smallest scale keeps its secret locked away, guarded by the deepest laws of physics perhaps forever beyond our direct sight. But sit with what that really means, because it is not a sad ending, it is a thrilling one. It means that right now, in front of your face, in the empty air between your hands, there is a mystery as deep as any in the cosmos. The bottom of reality is hidden in every tiny gap, in every speck of space, everywhere. All the time, you're surrounded by the greatest unsolved question in science, wrapped around you closer than your own skin. Think about that the next time you look at empty space, that nothing is not nothing. Down at the smallest scale, it might be boiling or woven from threads, or humming with hidden energy, or stitched from invisible links, or built from tiny events, or made of information, or something no human has yet imagined. The floor of the universe is right there, and we still do not know what it is made of. That is what makes this the greatest adventure of all. The smallest scale of space holds the deepest secret of reality, and the story is not finished. Somewhere out there, maybe in a lab today, maybe in a mind not yet born, the answer is waiting. And when we finally learn what space is truly made of, we will finally understand what everything, including you, is built from. The journey to the bottom is not over. It has only just begun.